Well friends, today I am going to talk about plasma response to fields. These could be external fields or self fields produced inside the plasma. And the basic formalism would be involving the fluid equations. So today I will give you a brief derivation of equation of motion, equation of continuity, and these will involve the concept of momentum loss via collisions and force experienced by particles due to pressure gradient. Well, these are the references, 3 books, one by F. Chen, the other one by V.L. Ginsberg, and the third one is by Thomas Sticks. Well, the plasma response, as you know, plasma comprises 3 kinds of species, namely the electrons, ions and neutrals. Neutrals are largely atoms, sometimes in some cases they may be ions, molecules also, but we will consider primarily the atoms. Now, these species are characterized by some macroscopic quantities like density, then mass of a carrier or particle, then charge of the particle, then we talk about the drift velocity, and the temperature. For electrons, we write these quantities as density as n, mass as m, charge as minus e, drift velocity as v vector, which is the average velocity of particles, and temperature as T, sometimes we will write as Te. For ions, density will be denoted as Ni, mass as Mi, charge as Zi into E, where Zi is called the charge number. For singly ionized ions, Zi is unity, drift velocity as Vi, and temperature as Ti. For neutrals, the density will be designated as N subscript N, mass as M subscript N, which will be nearly equal to Mi, mass of the ion, charge of the neutrals is 0, drift velocity often will be 0, sometimes this may be finite, so we will refer that later, and temperature of the neutrals will be Tn. So, these are the macroscopic parameters that characterize a species. The SO is that when we apply an electric field, for instance, what is the equation that will govern the drift velocity of particles, what is the equation that will govern the evolution of density of particles. These 2 quantities N and V are characterized or governed by 2 equations. They are known as the equation of continuity and equation of motion. Let me begin with the equation of motion. Equation of motion for instance, I will write the equation of motion for electrons, which says that rate of change of momentum m dV by dt is equal to the applied force or force experienced by the particle. Now, the force can be of many kinds. If there is an electric field in the system, then and magnetic field in the system, then the F would be equal to charge of the electron into the electric field E, and if there is a magnetic field, the force will be minus E, the charge, into V cross B. So, this is known as the electromagnetic force on the particle, on the electron. Besides this, there is another force on the electron that could be due to collisional drag. The collisional drag, let us understand what is this. When the electrons move, they acquire a drift velocity, then this on their way they encounter a heavy particle, means an ion or a neutral atom. For instance, this is a particle here, ion, electron is coming from here. As it comes close by, it experiences an attractive force and its path gets deviated like this. So, the electron which was coming like this, after passing through the vicinity of the ion, has changed its direction of momentum. So, there is a loss of momentum or momentum change in each collision. What we do? We say that on an average in a collision momentum is randomized, means in some collisions the change of momentum is negligible, in some the change of momentum is 2 mv. If electron is coming with a momentum mv, then the change in momentum per collision is approximately equal to mv. Change in momentum per collision is equal to mv, and if there are new collisions per second, then the momentum lost in collisions per second will be nu times mv. So, momentum lost in new collisions per second this would be equal to mv into nu, but this is a loss of momentum, not gain of momentum. So, equivalent collisional drag force on the electron would be F due to collisional drag would be equal to minus m nu v. This I have written in the assuming that the scatterer, the ion or neutral, is not moving. In case there is a drift of the scatterer particle, then this is modified by for collisions with particles moving with drift velocity Vi, for instance, the F due to collisional drag would be minus m nu into V minus Vi. So, this is an important loss mechanism for momentum. So, electrons gain momentum from electric and magnetic fields, but they lose momentum via collisions to ions and neutral particles. Usually Vi is small as compared to V, and we can ignore this Vi here, but in some cases this is required. So, unless we are considering a case where ion velocity is significant, we will be essentially using this expression m nu v for momentum loss per collision per second. Then there is another force on the electrons, because they have finite temperature and hence they possess finite partial pressure. Partial pressure of electrons is written as product of electron density into temperature of the electrons. Here Boltzmann constant is hidden in Te. So, basically you are familiar with pressure of a Maxwellian gas as product of density into Boltzmann constant and temperature. For electrons, density is N, and Kt we call Kbt we call as simply Te. This is temperature and energy units. Now, the problem is that when you apply certain fields on the particles, especially the fields of waves, the particles acquire drift velocity, and the velocity is not uniform everywhere, it may vary from point to point. As a result, density may change, so pressure will change. The issue is, if there is a non-uniformity in pressure, I will call this pressure as Pe, for instance, is a scalar quantity. Now consider a simple case. Suppose I consider a region of space of unit area of cross section, this is unit area, and the distance between this is, say, delta x. So consider a volume of plasma of unit area of cross section and length delta x, and suppose the pressure varies with x. So pressure on the left is Pe and pressure on the right is Pe plus delta Pe, because the pressure is changing, so it will be different here than there. Now what the pressure does? Pressure means the force exerted by the gas on the left on this, so this force will be in this direction, whereas the gas or the electron gas on the right hand side will exert a force in the leftward direction. So the rightward force is Pe, leftward force is Pe plus delta Pe, and hence the net force on the volume element is equal to minus delta Pe in the x direction. But how many particles are feeling this force? The number of particles that are contained in this volume, if n is the density of electrons in unit volume, then the volume of this small space is this region, the volume is 1 into dx. So the total number of particles here would be density times delta x. So the force per particle per electron would be then minus delta Pe divided by the number of particles in this volume element, which is n times delta x, and that is in the x direction. This is written as minus 1 upon n delta delta x of Pe, and Pe is Nt, so it's n times Te. So this is an expression for the pressure gradient force experienced by each electron. So now we have found typically 4 forces that an electron will experience, and I can summarize them F as the electric force, the magnetic force V cross B, then there is a force due to collision drag which is m V nu, and then there is a force due to pressure gradient which is minus 1 upon n gradient of Nte. Here I have generalized the pressure gradient force. In my derivation I had presumed that the pressure varies only with x, but if pressure varies in general with x, y, z, then the force will be expressed as a gradient of pressure. Now the issue is, on the left hand side of the equation of motion we had m dV by dt. What is dV by dt? Let us understand this. Please, we are dealing here with millions and trillions of electrons in a system, in a plasma. There are a lot of particles, and we are talking about average velocities. But the system may not have the average velocity. If you take average velocity of particles in this region in a small volume around this point, it could be different. Somewhere here it is different. Then if you consider a volume element here, so number of particles here, if you count and measure their velocities and take their average, the value of V will be different here than there. So rather than specifying the velocity of an individual particle, we define V as a quantity called velocity field. This means that I can divide my system, my plasma, into a large number of small volume elements, and in each volume there may be large number of particles. So, find their average velocities, but this average will depend on time as well as position. So, this velocity field is the average velocity of particles located at position r at time t. If you have a function which depends on one variable, then you can define the differential coefficient of that function. Simply, suppose there is a function, say g, some function of x, then we define dg by dx as limit x going to 0, g at x plus delta x going to 0 rather, minus g at x upon delta x. This is the definition of differential coefficient of a function of one variable. Here we are dealing with velocity field, which is a function of r and t. R means x, y and z. So, 3 variables, and t. So, it is a 4 variable function. So, here we have to be careful about defining the differential coefficient. Now, total time derivative implies that if you are obtaining dB by dt, then what should you do? Measure the velocity of an electron at r position at time t. Suppose this is my volume element RT, located at RT. So, consider the number of particles here, find their average velocity at time t. After a while, these particles, because they are moving with a finite drift velocity, so they have moved out somewhere here. So, this position would be moved by distance delta r, which will be equal to v velocity times delta t. So, rather than obtaining the velocity at time t plus dt here, you measure the velocity at this time, at this position. So, find the velocity at position r plus v dt, because this is the new position, this particles have moved, and at time t plus delta t, and take the difference of this velocity here from the velocity that was here. So, your eye is fixed on the same particles which were here, then they have moved to the here, and divide this by delta t, and then take the limit delta t going to 0, tending to 0. So, this is the definition of total time derivative. In contrast, if I had kept my eye fixed at this point, measured the velocity of particle at position r at time t, and then later at same point at time t plus delta t, I will get a quantity called delta b by delta t, which is the limit delta t tending to 0. I am keeping my eye fixed on the volume element. So, v at r at time t plus delta t minus v at time at position r at time t upon delta t. Please understand one thing, that my eye is fixed on the volume element, not on the particles, when I calculate the partial time derivative of v. So, these two derivatives are different. This is called total time derivative with respect to time. This is called partial time derivative of velocity. They are not equal, they are not same. Now, we can understand that this v is a function of 4 variables, and we can employ Taylor expansion to simplify this expression. I will do that. So, I can write simply v as a function of x plus Vx delta t, y plus Vy delta t, z plus Vz delta t, comma t plus delta t. This is my V at position r plus V delta t and t plus delta t. I am using the Taylor expansion. This gives me, because this is a function of 4 variables, so I will differentiate V with respect to each variable one by one, delta V by delta t into change in variable t, which is by delta t. This is the first thing. Then I differentiate V with respect to this variable. So delta V upon delta x into increase in this variable by amount Vx delta t, plus the next variable is y. So delta V upon delta y Vy delta t. The last one is variation with respect to z. So delta V upon delta z into Vz delta t. Now delta t is common in all of these, so I can take it common and I can write this as delta V by delta t plus Vx delta V by delta x plus Vy delta V upon delta y plus Vz delta V upon delta z. Now delta delta x, delta delta y and delta delta z are 3 components of del operator. So I can write this in a simpler way as gradient delta t multiplied by delta V by delta t plus V dot del and V. And if I use this in my definition of dV by dt, I obtain dV by dt is equal to delta V by delta t, because I have to divide this. Sorry, I forgot one thing very important. This is the change in V, but I should write this a term here. I should have added a term here, which is V at r and t, the initial value. I forgot to write that. I am sorry with that. So just add this term here, plus V at r and t. So plus V at r and t plus V at r and t. So when you substitute this in the definition of dV by dt, it turns out to be delta V by delta t plus V dot del V. So there is a connection between total time derivative and partial time derivative. This is the additional term that comes over here. It is called convective derivative. This term is finite only when velocity or its average velocity depends on position. If you apply a uniform field to all the electrons in the plasma, and if V does not depend on position, then obviously this term is 0. So whenever your force that is producing the average velocity is space dependence, then this term may be important and one has to be careful. One cannot ignore it. So well, this is the total time derivative of velocity, and now I will use this in the equation of motion and write the equation of motion like this. So equation of motion can be written as m delta V by delta t plus V dot del V is equal to minus E minus E V cross B the magnetic force minus m nu V collisional drag force and minus 1 upon n gradient of n Te, the pressure gradient force. This is our complete equation of motion. Well, in some cases, like if you are talking of plasmas in stars and like sun, then there is a gravitational force also. So, to the right hand side one must add a term. If gravity is there, say gravity is g, then plus mg, a force due to gravity should also be added there. But in most laboratory plasmas of interest, mg is not significant. You can ignore this, and hence we will be dealing largely with these terms, remaining terms in this equation. But in some cases of interest, we will be adding this mg term also. Now, this is one equation which has been very widely used. You may note one thing. It will be simple. Suppose the plasma has only electric field. Forget this magnetic force term, forget the gravity term, forget the pressure gradient term, and suppose the collisions are not there, then forget this term also. Then the response of electrons to an electric field is given by this equation. V is called the response and E is called the source that acts on the particles. The thing is that the response has a single term V here, but it is a product of response terms. This product of V's is called nonlinear term, and this is a typical characteristic of plasmas that in many applications these nonlinear terms become important, and this is largely the source of nonlinear phenomena like harmonic generation, parametric instabilities, and many other phenomena. Similarly, if there is a magnetic field of the wave, for instance, then this V cross B term you cannot ignore, and this also is called nonlinear term because the force involves the response itself. So, whenever this is a product of response to the source, then the term is called nonlinear term, and this also is responsible for a large number of phenomena, nonlinear phenomena. Sometimes the product of density and temperature may cause nonlinearity, or collision frequency with velocity product, because collision frequency also depends on velocity of the particles, not only average velocity but on thermal velocity also. So, they are also sources of nonlinearity in plasmas. So, basic thing is that plasma response in general to any field is nonlinear. However, if the fields are weak, you can ignore the nonlinear terms, and the process of neglecting these nonlinear terms is called linearization. So, we will solve these equations in a little while. However, let me go over to another important equation, and that is called the equation of continuity. Equation of continuity can be written as rate of change or partial rate of change of density with time delta n by delta t plus divergence of nv is equal to 0. I think I need to explain a few things in here. What is nv and why this divergence of nv is related to density? Let me explain this. This product of nv is usually called the flux of particles, and let me denote this by Fe, a vector which is equal to nv. Let us understand what is this quantity. Suppose electrons have an average velocity in certain direction. Suppose this is the direction of average velocity of electrons. Consider a unit area perpendicular to V. A question would arise, how many particles will cross this area in 1 second? V is the average velocity with which the electrons move. means the distance they travel in 1 second. So, all those electrons which are at a distance equal or less than v will be able to cross this, because in 1 second they will travel a distance v. So, what you are expecting is that in 1 second all those particles that are filled in a volume of length unity, of area of cross section unity and length v, they will be able to cross this. And how many particles are there in this volume? The volume of this space is, this region is length v into cross section 1. So, volume is 1 into v, and the number of particles in this would be number of electrons in this volume would be electron density n into volume of this region, which is v. So, this is the flux. So, flux essentially implies the number of particles crossing unit area per unit time if they are moving with the drift velocity v, because it is a vector quantity. So, we call this F e as n v, as I had written above. So, this is called the particle flux crossing unit area per unit time. The issue is, in a system, if this quantity is not uniform, it varies. To be simple, consider a region. Let me go to the next page. Consider a small volume of unit area of cross section and separation of width like delta x, and suppose the velocity is in the x direction. So, this is my velocity Vx. If particles are flowing here with a flux Fe, the flux with which they are moving out could be Fe plus change in Fe. Suppose the change in Fe is delta Fe. So, the number of electrons entering per second this volume element is Fe, the number of electrons leaving this unit area per second is Fe plus delta Fe. So, if this is quantity is positive, more particles are leaving, less are coming in, and hence there is a net reduction in density particle number here. So, net reduction in electron number in the element is equal to delta Fe per second. Is delta Fe, and the total volume is how much? Unit area I am considering. So, area of this element is delta x. So, this is the number of electrons reduced in volume delta x. So, net reduction in electron density or electron number, in an electron number per unit volume per second would be delta Fe upon volume, which is delta x. I can write this quantity as delta x of Fe, but Fe is a product of Nv, and V, as I am taking in the x direction, will be Nvx. You can generalize this to 3 dimensions rather than considering a volume element perpendicular to x axis. It is in a general direction, then particles are entering there. The volume elements could be a box like this. So, particle can enter and leave. So, in 3 dimensions when particles are moving, then the net number of particles reduced per unit volume is gradient of NV. Please understand, this quantity is the reduction. So, if I have to write the increase, then I should write a minus quantity. Whenever this quantity is negative, then there is an increase. When more particles enter, less leave, then there is an increase. So, in that case a negative, so then just put this equal to rate of change of density, and this is precisely the equation of continuity. So, the equation of continuity, let me rewrite as delta n by delta t plus divergence of, sorry, there is a dot product required here, n v is equal to 0. So, I think I have given you a simple derivation of 2 important equations in plasma dynamics that controls the plasma dynamics, the dynamics of electrons, and similarly you can write the equations for ions also. So, we treat ions as a mixture of 2 fluids, electron fluid and ion fluid, and you write separate equations for electron density and electron velocity, and similarly ion density and ion velocity. But whenever the electrons move, they constitute a current. So, when there is a current, then the current will produce from Maxwell's equations magnetic field and electric field, or whenever charges move, they also produce electric field, even if the density is there. So, when there is accumulation of charges somewhere or rarefaction of charges, that will produce electric field. So, one should combine these equations, the equation of motion and continuity, with the Maxwell's equations, and then they form a complete set to describe a system. So, let me write down the Maxwell's equations also to complete our description. So, I am going to just briefly mention Maxwell's equations. The first equation is known as divergence of D is equal to rho. Now, D is relative to the electric field through this relation. By definition, D is equal to epsilon 0 E plus polarization capital P. In gaseous plasmas, the polarization of atoms is very small, and you can ignore this capital P term. So, for gaseous plasmas, this is typically of the order of epsilon 0 into E, where epsilon 0 is called free space permittivity. This is free space permittivity in MKS units. So, this displacement vector is related to electric field by this quantity epsilon 0 E. Another equation is the divergence equation for magnetic field B, which says divergence of B is equal to 0. B is the magnetic field. Third is the equation equivalent of Faraday's law of electromagnetic induction, which is curl of E is equal to minus delta B by delta T. In integral form, this equation sometimes is written, and this is written as E dot dl, this quantity over a closed path is called EMF. Just line integral of the electric field is equal to rate of change of flux linked with the circuit. So, this is B dot ds is the flux linked with the circuit and rate of change of flux with time. And the fourth Maxwell equation is generalization of Ampere's law, which says that curl of H is equal to J plus delta D by delta T. J is known as the current density and H is related to the physical quantity B, the magnetic field. By this relation, B is equal to mu 0 H plus M, where H, well, mu 0 is the magnetic permeability of free space and M is the magnetization or dipole moment per unit volume. For plasmas, this M is negligible and this is equal to mu 0 H. So, this is called free space permeability. So, these 4 Maxwell's equations coupled with the equation of motion and continuity form a complete set of equations governing the dynamics of plasmas. Well, I would like to caution that these equations, though they describe the plasma dynamics in most situations, but still they are missing some important effects called kinetic effects, because when we are dealing with the propagation of waves in particular, some electrons may be moving with the velocity of the wave, phase velocity of the wave, and they can interact very resonantly with the waves and can exchange momentum and energy with the waves very effectively. So, we have to deal with different electrons moving with different velocities differently, and for that one requires a kinetic description or the description based on velocity equation. When we come to that stage, we will discuss that equation also. Well, so I have given you 4 Maxwell's equations that in conjunction with the equation of motion and continuity complete the description of a plasma, many phenomena in plasmas. However, before I close, I would like to say a word about collisions. So, a word on collisions will be proper at this stage. Well, what happens that when an electron moves in the vicinity of a scatterer, if the electron moves quite far away from the scatterer, it does not suffer a collision, it goes like this. But when it falls within certain distance, the distance of closest approach is called impact parameter. For instance, if I have a typical radius of an atom like A, then you can characterize the effective area of cross section of the atom to be Q is equal to pi a square. So, whenever the electron falls on this area, it will suffer a collision, and after collision it will go like this. If it moves away from this area, then it suffers no collision. So, for electron neutral collisions, you can always assign a effective area with the atom. Now, I would like to see the problem in a different way. Rather than assigning a area to the scatterer, I am assigning an effective area of cross section to the electron. Suppose the electron has a halo around it of cross section Q, and when the electron travels a distance in 1 second is like thermal velocity V thermal. So, in 1 second it will move like this, but before it covers 1 second it may collide with an atom and it may change its path, it may go like this. So, the electron comes here and suffers a collision and goes in this direction, then suffers another collision and goes in this direction. Now, the mass of the electron is very tiny as compared to the mass of the scatterer. So, primarily the energy transfer is very little, the moment transfer is the significant quantity. So, these are called momentum randomizing collisions. So, what I can say that if the electron is moving a distance of the order of V thermal velocity or thermal speed in 1 second, So, it will traverse a zigzag kind of cylinder of cross section q and length v thermal, and the number of collisions it will suffer in 1 second is the same as the number of scatterers it will encounter on its way, because the scatterers which are outside will not collide with this. So, only those scatterers which are lying inside this cylinder, they will be colliding with this electron. So, what is the total volume of this electron cylinder? Volume of the cylinder, which is a fictitious cylinder of cross section q that I am assigning to an electron. The length is v thermal, cross sectional area is q. So, q into v thermal is the volume, and in this volume how many scattering particles will be there? Scatterer will be there. If the neutral particles have a density Nn, then the number of scatterers in this cylinder would be equal to their density into volume, and this quantity is then called the collision frequency, because with each particle electron is going to suffer a collision. So, the number of collisions, so the collision frequency nu is equal to Nn q into v thermal. This is the collision frequency, is a product of density of scatterers into collision cross section of the scatterer into thermal velocity of the electron. For neutral particles, q is simply equal to pi a square, where a is the radius of the atom, which is of the order of an angstrom or few angstroms. So, q is typically 10 to the power minus 19 meter square, but the case of collisions of electrons with ions is very different. Let us understand that also. In the case of ions, ions exert a force on the electron even if it is quite far away from here. Obviously, if the distance of closest approach, suppose the electron is going like this, then the distance of closest approach is called impact parameter p. If this is electron is coming closer here, this will not go on this path, it will go like something like this, it will feel attracted and go like this. This is the actual path the electron will traverse, and you expect that larger the value of p, weaker the effect of this electron attractive force or Coulomb force of the ion on the electron. So, the change in momentum or change in direction of the electron motion will be less effective when p is large, but p could be quite large, not a angstrom, it could be several angstroms, tens of angstroms or hundreds of angstroms, because this is a slowly varying the potential or the electrical force due to the ion on the electron is a long range force. So, but how to define a effective collision frequency? We define an effective collision frequency by saying that find out the impact parameter p for which the electron suffers a 90-degree collision. It means it goes like and comes like this, so that the angle of scattering is 90 degrees. And what has been found is a simple calculation, that impact parameter p for which the kinetic energy of the electron, which is half mv square, equals the potential energy due to the ion. If the ion charge is Zi into E, electron charge is small e, then this quantity divided by p, 4 pi epsilon 0 into p, is the potential energy. So, if I equate the kinetic energy of the electron to potential energy of the electron at the impact parameter p, then the p that you get from here turns out to be the one that if an electron arrives with impact parameter p given by this equation, it suffers a 90-degree collision. So, we define an effective area of cross section q is equal to pi p square, and if you put the value of p from this equation, it turns out to be P is equal to, so pi is there and 2 will cancel out. So, you will get Z I E square upon 2 pi epsilon 0 m whole square into 1 upon V4. This is a very V thermal rather, this is thermal velocity. I am presuming here that my electron is moving with a velocity, actual velocity is, this V really is the actual velocity. Here I am presuming that the actual velocity is like thermal velocity typically. Some electrons may move faster, some may move slowly. So, we are typically taking this like thermal velocity. So, collision cross section Q is inversely proportional to fourth power of velocity. How about the collision frequency? Collision frequency is a product of ion density, collision cross section and thermal velocity. So, when you put these numbers in here, this scale says thermal velocity of electron to the power -3 or temperature of the electron to the power -3/2. This is a very important dependence, means the electron temperature, larger the electron temperature, weaker the collision frequency. And later on we will learn that all major quantities like electrical conductivity, thermal conductivity, diffusion coefficient, etc. These macroscopic quantities depend on collision frequency and hence they depend on electron temperature very sensitively. This is a very important dependence. So, whereas for the case of electron neutral collisions, collision cross section Q was a constant. If Q is a constant, then the collision frequency will increase with thermal velocity like temperature to the power half. Whereas in a electron ion collision, because Q decreases with velocity of the electron, so collision frequency scale says -3/2. This is something very significant, and we will see its effect on response of a plasma to electric field later. Thank you very much.